Welcome back, everyone. I'm sorry for a little delay here, but we are back to our last part of today training. So I'm going to show you now a very quick example of a controller hardware in the loop. And okay, let's start. The first thing I will want to show you, so I hope you can see in the webcam now that I have here a C-HIL 402 and also a microgrid board with a DSP, a Texas Instrument 28335 that we are going to use to demonstrate here how can we run a controller hardware in the loop with Typhoon system. Okay, so if you can see here in my screen, I have a model of a NPC 3-level 3-phase converter. So let's see what we have here. Basically, we have a grid simulator which simulates the grid with some measurements. We have two contactors, one used for pre-charge. So when we connect to the grid, we limit the current, and bypass one. So that's when we are actually connected fully to the grid. Also, we have an LCL filter. And here we have our NPC inverter. We can double click it, and we can check here that we are using digital inputs for switching it, and these digital signals are connected to our PWM outputs here of the DSP control card. And we are here now in the DC link having a constant DC source with two capacitors for splitting the DC link in half. And basically, we have implemented here. Let me show you some of the code. All right, but basically, what we have here in this control is a power control which controls power, active power, and reactive power, and also a DC balancing control, which makes sure that these two capacitors are have equal voltage, equals to half of the DC voltage. So let's compile this model. So we can already see that we are running this simulation with a half microsecond time step. And now we are already here in our C-HIL SCADA. Let's just open the pre-built C-HIL SCADA that we have, and let's load the simulation settings. Okay, what we have here in the screen, some widgets for grid control, so we can switch between harmonics and pure sine, with some controls to change the voltage. We have some plots of grid voltage and frequency, inverter control, power measurements at the point of coupling. Also, we have here measurements of active power and reactive power, DC link measurements, and the control for power references. So the most important thing as we are concerned in a hardware in the loop controller is this. We have our configuration of analog outputs to the DSP. So we have grid currents, converter currents, filter capacitor voltages of the filter, grid voltages, and grid currents, as well as the DC capacitor voltages. So we can do the DC link balancing. We don't have any outputs going on to the DSP. And you can see here in the power references that actually we are setting digital outputs for the DSP depending on our settings. So this is the way we send the power references to the DSP, and hopefully it will control power according to the references. So now let me just turn off the C-HIL. Let me just connect the board. All right, now it's fully connected. Let me turn the C-HIL on again. And maybe you will see, that the DSP is off because I have this switch here that I can turn it on. So let's just reload the model here now. Let's reload settings. And let's see what happens if I play the simulation. Just set this to 0. Okay. Let me go to scope. And we see that nothing happens. That's because our DSP is not turned on. So I have already downloaded the control code here. And now I can turn it on and I can see what happens. All right, so our system is working. We have here a power set point of 300 kilowatts, which is basically being controlled very nicely. We can see here almost perfect control. In the DC link, we can see that this voltage stays around 500, which is the half of this voltage. So we can change here the references and see the controller in the DSP running this in real time. Let's change reactive power. So this works nicely. Another feature of this controller is basically we have a resonant controller which rejects harmonics from the 5th, 7th, and 11th. And we can see here that we can change harmonics for the grid. Now it's pretty much distorted, and currents are still sinusoidal. So we're not injecting a distorted current into the grid. Another thing that is implemented here is a startup procedure. So let me just turn off the DSP again, and let me just capture the starter procedure. I'm gonna capture for 10 seconds. So let me force trigger and turn on. You can see here DC link starts diverging when DSP is not turned on, and then when it turns on, then voltage starts to be controlled. But let's see our startup sequence. So we can see here that we first turn on the pre-charging contactor, then we turn on the bypass of the pre-charging contactor, and later on, after 5 seconds, we ramp up the currents and power set points. So we have a very good transient starting point. And as I said, everything is implemented in the DSP. Another thing that we have implemented is a low voltage write-through specification. So one of these specifications is that if the grid voltage is under 0.7 pu, it must stay connected for 10 seconds, and then it should turn it off. So let's check it out. Here, let's turn this to 0.6. Let's wait around 10 seconds to see if currents go down. So here we have it, low voltage right through. And when we make it go back to 1, to around 1, so we have all the startup sequence again. So we wait 5 seconds, and there we go. We have our currents. So this was a very simple example of a real grid-connected NPC 3-level 3-phase inverter running on a Texas Instrument DSP with one of our TI boards connected to a HIL. I'd like to say that this controller of this converter was designed by a collaboration that Typhoon had with Professor Humberto Pinheiro from Federal University of Santa Maria in Brazil. So we really thank them for the fruitful collaboration, and now we can have some very good examples as you have seen now today. So I hope you enjoyed. If you have any questions, please ask in the GoToWebinar. And now let's give a very short break so we can go back to wrap up. Thank you very much.